Welcome to this episode of the CompTIA Tech Plus Prepcast by baremetalcyber.com. Let's begin. Databases store, organize, and retrieve information in specific formats, and their structure determines how well they perform, scale, and adapt to different needs. The way a database is organized impacts its speed, flexibility, and the effort needed to maintain it. For the Tech Plus certification, you will need to recognize structured, semi-structured, and unstructured data models and understand their role in both relational and non-relational systems. In this episode, we will compare these structures and explain how each applies to real-world IT scenarios. Structured data is information organized into well-defined tables with specific fields and data types, making it predictable and easy to search. Semi-structured data contains some organization, such as tags or markers, but does not fit neatly into a rigid table format. Unstructured data has no predefined model, including things like raw images, audio, or free-form text, which require specialized tools to process. The right structure depends on how the data will be collected, queried, and analyzed, as well as the performance requirements of the system. Structured data relies on schemas to define exactly how information is stored, including its data types, relationships, and integrity rules. Because it fits neatly into rows and columns, it can be queried efficiently using structured query language, or SQL. This format is widely used in business applications for tasks such as managing customer accounts or processing financial transactions. Structured designs also make indexing and reporting faster, supporting high performance in environments that need precision and consistency. Relational databases are systems built to manage structured data by organizing it into related tables. Each table represents an entity such as users, orders, or products, and relationships between them help reduce redundancy and allow powerful cross-referencing. By linking data logically, relational databases ensure that updates in one place are reflected wherever that information is used. Common platforms include MySQL, Postgres, Oracle, and Microsoft SQL Server, each offering mature, enterprise-ready tools. In a relational database, a table stores data for a specific category, with each row representing a single record and each column storing a specific attribute of that record. For example, an employees table might have rows for each worker and columns for name, job title, and hire date. All records in the table follow the same structure, which ensures consistency and makes it easier to retrieve, compare, and report on data across the organization. Keys and constraints are essential to relational database design. A primary key uniquely identifies each row in a table, ensuring no duplicates exist. Foreign keys create links between records in different tables, enforcing relationships and keeping data consistent. Constraints set rules for allowed values, such as requiring certain fields to be filled or restricting entries to unique values. These features maintain data integrity and support the relational logic that underpins the system. A schema defines the complete layout of a database, including all tables, fields, keys, and the relationships between them. Relationships can be one-to-one, one-to-many, or many-to-many, depending on the nature of the data connections. Well-designed schemas not only enforce consistency and validation, but also make querying easier and more efficient. They are essential for ensuring that all users and applications interact with the database in a predictable, reliable way. Relational databases are accessed and managed through structured query language. SQL allows users to retrieve, update, insert, or delete data using a specific set of commands. It supports complex operations, such as joining data from multiple tables, filtering results, and grouping information for analysis. Efficient queries require a clear understanding of table relationships and indexing to minimize processing time and resource usage. The benefits of relational structures include consistency, accuracy, and high-speed access to structured data. They are designed for environments where precision is critical, such as finance, healthcare, and government systems. Relational databases handle complex queries well and support many users accessing data simultaneously. Their maturity and widespread adoption mean there is a large ecosystem of tools, documentation, and skilled professionals available to support them. However, relational databases are not without limitations. The fixed nature of their schemas can make it challenging to adapt quickly when data requirements change. Scaling horizontally across multiple servers can also be complex, and they are not well suited for highly variable or unstructured data such as social media feeds or raw sensor readings. Modifying the schema often requires downtime or careful coordination to avoid disrupting dependent applications. Non-relational databases, often called NoSQL databases, take a different approach by supporting flexible data models that can handle structured, semi-structured, or unstructured information. They are commonly used for managing large-scale or rapidly changing datasets, especially in real-time analytics, IoT deployments, and content management systems. Types of NoSQL databases include document, key value, columnar, and graph databases, each optimized for specific workloads and access patterns. Document databases store data in self-contained units, often in JSON or BSON format, where each document can have a unique structure. This flexibility makes them well-suited for web applications and content platforms, where records can vary widely. Examples include MongoDB and Couchbase, which allow developers to store and retrieve information without the strict structure of relational tables, while still supporting indexing and querying for performance. Key value stores focus on simplicity and speed by storing data as pairs of unique keys and their associated values. Keys act like identifiers, and values can be any type of data. Because retrieval is based directly on the key, these systems are extremely fast and are ideal for use cases such as caching, managing session data, or quickly storing temporary results. Popular key value stores include Redis and Amazon DynamoDB, both of which are known for high performance and scalability. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Columnar databases organize information by column rather than by row, making them especially efficient for analytical workloads where only certain fields need to be retrieved. By storing all values of the same type together, these systems can compress data more effectively and reduce the amount read during queries. This design is ideal for business intelligence platforms, reporting systems, and data warehouses, where performance gains are measured in the speed and scale of analysis. Common examples include Apache Cassandra, HBase, and Amazon Redshift. Graph databases represent data as nodes and the relationships between them as edges, focusing on how items are connected rather than simply how they are grouped. This model is highly effective for representing complex networks such as social media connections, organizational structures, or recommendation engines. By storing relationships as first-class elements, graph databases make it possible to run queries that reveal connections quickly and intuitively. Popular systems include Neo4j and Amazon Neptune, both designed for high-performance relationship mapping. Non-relational databases offer several key advantages over traditional relational systems. Their flexible schemas allow for changes to data structures without downtime, making them ideal for rapidly evolving projects. They are also better suited to handling unstructured or semi-structured data, scaling horizontally by distributing data across many servers. Applications that prioritize availability and speed over strict transactional consistency, such as streaming platforms or large-scale IoT deployments, often benefit most from these systems. However, non-relational models have their own limitations. The lack of a standardized query language means that tools and skills are often platform-specific, making cross-system integration more challenging. Compared to SQL-based systems, tooling and ecosystem maturity can be less developed. Additionally, because data relationships are often managed in the application layer rather than the database itself, complex transactional integrity can require custom solutions. These trade-offs must be considered when selecting a database architecture. When comparing relational and non-relational structures, the choice depends largely on the nature of the data and the business requirements. Relational databases are optimal for structured, highly transactional environments that demand precision and consistency. Non-relational systems shine when working with large-scale, dynamic datasets that require flexibility and horizontal scalability. Many modern organizations use both, employing hybrid strategies, where relational databases handle core records, while NoSQL systems manage unstructured content or high-volume workloads. Selecting the right database type requires evaluating factors such as consistency needs, scalability goals, performance requirements, and the expected structure of the data. If strict data integrity and complex relational queries are priorities, a relational database is the logical choice. If the workload involves dynamic content, rapidly growing datasets, or the need to store diverse formats, a non-relational option may be better. Skilled IT professionals can assess storage needs and recommend architectures that align with long-term objectives. Real-world use cases often demonstrate how these systems complement each other. An e-commerce platform might rely on a relational database to manage orders, payments, and customer accounts, while using a document database for its product catalog. A social media platform might use a graph database to map relationships and a key value store for fast session management. Business intelligence systems may use columnar stores for fast, complex reporting queries. Choosing correctly can improve application performance, reduce costs, and simplify maintenance. For the Tech Plus exam, be prepared to compare structured, semi-structured, and unstructured data and to identify the strengths and weaknesses of relational versus non-relational systems. You may see scenarios where you must recommend a database type based on the type of data and its intended use. Being able to match a system's capabilities to the requirements described in a question is key to answering correctly. Key glossary terms for this topic include schema, table, record, primary key, document store, key value pair, columnar store, and graph database. Reinforcing your understanding of relationships, constraints, and flexibility through flashcards or categorization exercises can help you quickly recall these terms under exam conditions. Grouping them by database type and function strengthens your ability to recognize their role in system design. In IT operations, understanding database structures benefits every role from system administration to application development. Support teams maintain access and monitor performance. Developers build features optimized for the chosen database type, and administrators oversee data integrity, backups, and cross-platform integration. A strong grasp of both relational and non-relational approaches helps IT professionals design infrastructure that is efficient, scalable, and aligned with business needs. In the next episode, we will move into backup strategies and storage locations, exploring how to protect data through redundancy, recovery processes, and appropriate storage choices. You will learn how to evaluate options such as local, external, and cloud-based systems, and how to align them with both operational requirements and risk management goals. Join us for Episode 48, Backup Strategies, File, System, and Storage Locations. Thanks for listening. Please visit baremetalcyber.com for more cybersecurity information and education, including a new children's series. For more information on books and more, follow us at cyberauthor.me.